Ri, okay, I between 1 and R, then the first non-zero entry is coming at a place which is Pi. All other entries on the left side are all 0. Okay, so that is the row echelon form of a matrix that we defined yesterday, and we proved a theorem that every non-zero matrix, again there is a typo, I should have corrected that. M cross n matrix can be reduced to a row echelon form using elementary row operations. So let me revise those elementary row operations. So these were the elementary row operations, namely you can interchange rows. First row can be interchanged with second, or second with the third, or first with the last, and so on. Any two rows can be interchanged. And second operation is adding one row to another. You can add one row to another. For example, the first row is added to the second. So what will happen? The first row will remain as it is. Only the second row will change. It will become R1 plus R2. And the third operation is multiplying a row by a non-zero scalar. So you are allowed to multiply by a non-zero scalar. Okay? So these are the row operations. They can be applied any number of times on the matrix. And basically, by applying this, we can reduce every matrix M cross n to a row echelon form. So let me just quickly give an example so that once again we are on the same page. This is a matrix given. Okay. So what is the process? We scan the first column. So scan the first column. The first non-zero entry is 2. So what we do? This 2, we want to bring it to the first place. So interchange R2 with R1. So the operation involved will be interchanging R2 with R1. So once that we are done, so our row will go up. So this 2 will go up. So 2, 1, 1, 1, 0. And 0, 0, 0 will come down. Okay. Right. And now what we do is we can make everything below this 0 by multiplying the first entry, that is 2, multiplied first this row by -3 and add it here so that this entry becomes 0. This will change. We don't bother about that. And similarly, we make this entry 0 by multiplying the first row by -3 by 2 and adding here. So that will become 0. So what will happen? This will be 2, 1, 1, 0, and 2 bottom below that everything will be 0. And these entries would have changed. That is okay. So that is step 1. Once that is done, you go to column number 2, okay, and do the same thing, but not from the ignore the first row, ignore the first column, and look at only the remaining part of it, and do the same operation. So let us do that. So once that is done, we will get after these operations, we'll get this. So this will be the matrix. As I said, it will be 2 here, 0 everything below. First row remains as it is. Things would have changed. Now look at this part. Okay, look at this part. Forget the first row, which we have already operated upon. This column. Look at this column from this one. There is 0 here and -1 and 1 by 2. So the first non-zero entry is coming here. So we'll interchange these two rows. So when we interchange this 0 will not affect. So this side nothing is affected. Only this -1 will go up. Okay, and that will change, and we go on repeating that process. So once we repeat that process, so the -1 goes up, -1, -2, 3, that goes up, 0, 0, 0 comes down, and then below that non-zero entry will make everything 0. So once again, this is already 0, so we don't have to do anything. For the bottom part, multiply this with multiply by 1 by 2 and add here, this will become 0. And go on doing. So elementary row operations, only the ones we specified, we are doing. So once you do that, this will become -1, right? This will become 0, 0. And now go to forget the second row, second column, look at the remaining. So that is 0, 3 by 2. So only this part is remaining. So this part, what we'll do is, because it is 0, scanning the third column, because this is 0, this is 3 by 2. So we interchange with that. Do the row operation of R3 with R2 in the last one. Oh, R3 and R4, sorry. Okay, so it gives you this. So that brings the matrix to row equivalent form. So let us check whether this is in the row equivalent form. So we have got this is a 1, 2, 3, 4, 1, 2, 3, 4, 4 by 4 matrix. And we've got a number R. R is equal to 3. 1, 2, 3. First 3 rows are non-zero. Bottom row is 0. So that number R is equal to 3. And what is P1? P1 is the first place where non-zero entry comes. So that is column number 1. So P1 is 1. P2 is the column for the second, that is P2 is 2 and P3 is 3. So P1, P2, P3, P1 is 1, P2 is 2, P3 is 3. So those are the numbers associated with the row equivalent form. Okay, so let me just indicate here. For example, if I do one more row operation here, I can multiply the last this row by 2. So this will become 3, and this will become 9 by 6, right? Multiplying by 2. And that new matrix also will be in a row equivalent form, because we have obtained it by a row operation. So that only indicates that a row equivalent form of a matrix need not be unique. Okay, but those numbers are P1, P2, PR are same for if matrix is in the row equivalent form obtained from the same matrix. So that is the row equivalent form. So now the question comes, we have got a process of making a matrix in the row equivalent form, which was motivated by the Gauss elimination method. And we said that matrices can be put on machine, and the machine, for example, a computer can do matrix multiplication, addition, subtraction, these things for us, are interchanging. So what we want to do is, how do we tell a machine that I give you this matrix, the data is with you, so how do you do the row operations? I can't just tell that look at the row 1 and interchange it with the row 10. So the matrix does not know really what is row 1 and row 10. It can do matrix multiplications, it can do matrix additions and so on. What we want to do is, we want to operate on the matrix, the row operations via matrix multiplication, right? So we want to transform, we want to generate a kind of algorithm. You can say that if I take a matrix and multiply it with some matrix, then it will do that row operation, whichever I want to do. So for that, let us define what are called the matrices for the row operations. For a matrix of order m cross n, identity matrix will denote it by Im. So Im will be the matrix of order okay, m by m. Okay, so let us write Eij. Eij denote the matrix where you take the identity matrix of order m cross m and interchange the ith row with the jth row. So interchange those two rows. Start with the identity matrix, interchange, you will get a new matrix Eij. Okay, so what we have done is, on the identity matrix we have performed a row operation, namely of interchanging two rows, interchanging ith and the jth row. So this is the identity matrix on the left hand side. Okay, this is the ith column, so that is 1. Jth row, jth column, that is 1, that is the identity matrix. On that, Ri operated with Rj, so this 0 will go up and this 1 will come down, and this 1 will go up and that 0 will come down. So that will look like in this place will be 0, In this place it will be 1. In this place it will be 1. In that place 0. So basically what we are doing is we are doing that operation of row operation on the identity matrix, and we get a new matrix, and that matrix we denoted by Eij. So we'll call this matrix as elementary matrix, and the lower I and j indicate that this is obtained from identity matrix by interchange of ith row with the jth row. Same things can be done for the other operations. So let us do that. So for example, multiplying ith row by a non-zero scalar alpha. So take the identity matrix, the ith row, okay, alpha I. So ith row, so this is the ith row. And earlier in the identity matrix, it was 1 here. Now multiply by alpha, you will get 1, 1, 1 up. And there it will be alpha, and the remaining will be 1 again. So this is the second type of elementary matrix obtained from the identity matrix by applying that elementary row operation of multiplying a particular row by a non-zero scalar. Okay. So the third was addition. So let us do the addition. So you can yet combine the earlier one also. So I plus ij. That means what? So that means take the jth row, multiply by alpha, and add it to the ith row. So adding its jth row to the ith row, multiplying by okay, here is a typo. I think you can take it as 1, alpha equal to 1, or you can write here alpha. It's the same operation that we do. So that elementary operation we are doing. So these three type of matrices are called elementary matrices. And what is the advantage of these elementary matrices? That these elementary matrices are very useful in the following way. So we are going to give an application of it. For example, let us just, for the sake of illustration, E12, right? E12 is ij. So 1 and 2 are interchanged. So this was actually the second row in identity that has become the first one. So that is E12. So E32C, okay, is you are multiplied the second by C, adding it to the third, so that is what you get. So multiply by C and add it here, so that is what you will get. So similarly, E lambda, so that is lambda 1. The first row is multiplied lambda. Okay. So the theorem that we want to state and verify is the following, that the product EJK A. So take any matrix A which is of order m cross n. Take elementary matrix of order m cross n. So that is m here. So we'll be multiplying on the left by these elementary matrices. So the matrix multiplication makes sense. So if you look at the product EJK times A, okay, A is any matrix of order m cross n, and you pre-multiply, that is multiply on the left by Ejk. What is Ejk? This is a matrix obtained from identity matrix by interchanging of ith, jth row by the kth row. So if you look at this product is same as A, except that the jth row of A and the kth row of A are interchanged. So what we are saying is pre-multiplying by this elementary matrix does that row operation of interchanging the jth row of A by kth row of A. And the same results are obtained by other elementary matrices. For example, if I do this, E lower I plus C times J, that means I have multiplied the jth column, so jth row by C, and adding it to the row I. That is the elementary matrix. If you pre-multiply A by that, then the resulting matrix will be nothing but the row of ith row of A would have changed to the ith row plus C times the jth row. The jth row will remain the same. And similarly, the third one is the elementary operation of multiplying jth row by a scalar alpha. So if you want to multiply the jth row of A by alpha, you pre-multiply by that matrix. These proofs of these are not very difficult to check. The only thing is one has to write down the elements of the two matrices and check that has the required properties. So, but let us just verify. So, writing a formal proof of this, I leave it for you to write down the formal proof. So, let us look at this matrix, which is a 3 rows and 4 columns. So I want to do some operation. Suppose we want to interchange the first row with the third row. I want to interchange this with this one. I want the computer to do it. Okay. So what I will do is I will ask the computer to look at the elementary matrix E first and third. So E13. So that matrix will be looking at the last one replaced by the first one in the identity matrix. So that, okay, and pre-multiply A with that. So E13 is the matrix. The third row has gone to the first has come to the third, interchange. So E13. And now if I pre-multiply A by E13, so I'll get the rows interchange. So 3, 2, 4, 6, that has become 1 first row, and 2, 1, 0, that has become. So that you can check multiplication. So these kind of illustrations you can always give, and you can check for particular examples. So everything is fine. So let me not spend much time on this. Okay. So what we can say is that theorem that every m cross n matrix can be brought to a row equivalent form is same as saying that there exists elementary matrices E1, E2, En, okay, of order m. M is the number of rows, such that if I look at A multiply on the left by that even some matrix, elementary matrix, depending on A. So there will be finite number of elementary matrices if I keep on doing that. So these correspond to the number of row operations which finally bring it to a row equivalent form. So in terms of metrical multiplication, the a row equivalent form of A will look like A multiplied, pre-multiplied by E1, E2, and En. So that is rewriting the process of bringing a matrix to a row equivalent form via matrix multiplication. Okay. One can actually continue doing this process a bit more. The first non-zero entry in row equivalent form is normally called a pivot. I don't know I said that or not, but anyway, the first non-zero entry in a row equivalent form in a row. So there was a number R. So first top rows are R rows are non-zero. So it has a first non-zero entry 0, 0, 0 somewhere A1 AI AI into AI PI. So that non-zero entry is a number. And what is the property of row equivalent form? Everything below that pivot is a non-zero entry, and everything below that is 0. So probably let me, this is the high time to write something and show you. So let me see where is my Windows journal. There it is. Okay. All right. So let me start using that. Is it visible to everybody?
Yes, sir.
Okay. Right. So so in the say if I look at Ri, is this much visible, or shall I make it slightly bigger?
I think it is fine.
Okay. So ith row looks like 0, 0, and there will be so this is first non-zero entry in the ith one will be AI at the place PI. So it will be PI column, and something will be there after that. So that is what the ith row in the row equivalent form looks like. This is the first non-zero entry. Okay. And if you look at the rows below it, right, they will all have 0. Do you agree or that not? I can make them even if they were not. So let us write that even if it was some entry here, some entry here, by a row operation, because this is a non-zero entry, right? I could multiply it with uh, suitable scalar so that and add so that this becomes 0. So I think I described that. So below that pivot, everything is 0. On the left, everything is also 0 in the row echelon form, right? And this entry, which is a non-zero entry, you can divide by that scalar and make it equal to 1. And not only that, you can make everything above that also equal to 0. Okay, that because that will not change this part of the matrix. Okay, so what we are saying is by doing some more elementary row operations, your matrix, each pivot, that is the first non-zero entry in the ith row, can be made equal to 1, and everything else in that column can be made equal to 0. So all other entries above each pivot is 0, can be made 0, and below also is 0. So that is the only non-zero entry in that column. The ith column, the only non-zero entry will be equal to 1. Everything else will be equal to 0. So if we do that on a row echelon form, then the matrix that we'll obtain is called reduced row echelon form. So that is called reduced row echelon form. Okay, so that is that means the row echelon form is further reduced to a special form where the non-zero entries are made 1 and everything else in that column is made equal to 0. And one can prove that we said that echelon form of a matrix need not be unique, but one can prove that now sort of we have normalized it, and reduced row echelon form of a matrix is unique. So that one can prove. Okay. I will not go into the proof of that because it's only a matter of writing various entries in a matrix. Okay. So in reduced row echelon form, this is the shape of the matrix that will look like. Okay. So this is a M cross N matrix. Maybe the first column is 0, second column is 0, this column is 0 up to P1. The P1th column is having a non-zero entry, and that is 1, and everything below that is equal to 0. Right? Below that, everything is equal to 0. Note that P1 is not equal to 1. P1 is here in this picture, P1 is strictly bigger than 1. P1, this could be 1. Okay, then P1 is 1. Here P1 is not equal to 1. And everything else in that column is 0. So if I look at the pivot, that is only non-zero entry, and that is 1, and everything below that is 0. Everything on the left is also equal to 0. Right? So now go to the second row. The first non-zero entry comes somewhere at this place. Okay, that is P2. And P2. So everything is the first non-zero entry, so everything that is 0. Okay, everything below that is 0, and this is a non-zero entry. Okay, so that is 1, and everything in that column is 0. And so what the structure of reduced row echelon form looks like. 0, 0, 0, 1, something we don't bother what it is. The second row 0, 0, 0, the place is on the right side, right? 0, 0, 0, that is 1 at the place P2 bigger than P1, and everything else is 0, and so on. Here is PR. Okay, the last entry where in the rth row something non-zero comes here, everything else is 0, and maybe afterwards something happens. So this is what the reduced row echelon form of a matrix looks like, and that is always unique. Reduced row echelon form is normally used in proving some theoretical results. And of course, when you want to compute inverses solutions, you will have to implicitly go for the reduced row echelon form. So this is what earlier example we showed. This is a given matrix, and this is this is a row echelon form. So I can make this entry as 1 by dividing this row by 2. This will become 1, and then this is 1, so I can suitably multiply and make this 0. And similarly, this entry can be made 1 and suitably multiplying, adding. This can be made 0 and this can be made 0. And similarly, the last one. Right. So this is what is called reduced row echelon form. So that is what it will look like for this matrix. Right. So this is the reduced row echelon form of the matrix here. Anybody has a question to ask till then now? Before I go further, if everything is clear? Right?
They are saying yes.
Yes, question or there is a question, yes, or it is clear, yes.
It's clear. Yes, I think.
Okay, fine.
Students?
Right.
Yeah, it's clear. Okay.
So let us go ahead and so the theorem says, given now I can sort of revise slightly for a special case when it is a n cross n matrix. If A is a square matrix of order n cross n, there exists elementary matrices E1, E2, En, so that we try to bring this matrix to reduced row echelon form, such that if I look at the reduced row echelon form, A multiplied by E1 up to E2, E2, En, then either how many pivots are possible maximum? It is less than or equal to the number of rows and columns. So here it is same. So possibly there are n pivots. And if there are n pivots, how does the reduced row echelon form look like? So let us just write it. How does it look like? So if this is a n cross n matrix and it's a reduced row echelon form, so that is A multiplied by E1 En, that is equal to reduced row echelon form. So if it is identity, that means what? That means this looks like along the diagonal 1 and everything else equal to 0. That is one possibility. Then when will that happen? If the number of pivots that R is equal to n, right? If the number of pivots P1, P2, P3, each row has got a non-zero entry, that will look like identity. If not, if it is not identity, then what will happen? This will not be 1, it will be somewhere, a 0 will be coming. There will be a 0 row coming if it is not identity. Okay. So that is what we are saying, that either it is identity or there is a last row which is 0. I think it's quite clear, obvious that this will happen. Because of the definition of pivots, the pivot is the only non-zero entry in that column. And if the number of columns having pivots is n, then either it is identity. If it is n, if it is less than n, then that means the pivots end up somewhere short of n. So there will be a row which is equal to 0 at the bottom. So that is what it should happen. Okay. So we are analyzing matrices only for the time being and the special forms. Okay. I think the proof is obvious. I don't have to. One has to only write 2 lines and let us omit writing the proof. So now let us start looking at some applications of this. The first one is going to be exploring inverse of a square matrix. So we say that a matrix, a square matrix is invertible if we can find another square matrix of the same order, say that AB is BA is equal to identity. And one proves that such a matrix is, if it exists, it is unique and is called the inverse of the matrix A. Right. So we want to explore this possibility So these are some elementary facts. Let us observe that each elementary matrix is invertible. That is an important thing for us for the time being. Namely, so what are the elementary matrices? They were multiplying a row by a non-zero scalar alpha. And why it is invertible? Because I can look at the matrix corresponding elementary matrix, which is dividing that particular row by alpha. So if I multiply with the 2, I'll get back identity, right? So it is inverse for elementary operation of multiplication by alpha, right? And similarly for others, if you are adding, you can subtract, right? Interchange, you can again interchange and go back. So because elementary matrices are obtained from identity matrix by doing something, and all these operations are reversible operations, so that basically tells you that they are invertible. For example, EJK, its inverse is itself interchange again, and similarly inverse of the other multiplying and adding, multiplying and subtract. Right, and multiplying by alpha, multiply by 1 over alpha. So these are the inverses. One can check that. Okay. So here is the important result from our point of view. A matrix A is invertible if and only if it is a product of elementary matrices. So we want to say a matrix is invertible if and only if two ways. If a matrix say is a product of elementary matrices, we just now observed each elementary matrix is invertible. So these matrices will be invertible, right? Product of invertible matrices is invertible. E1 invertible, E2 invertible, En invertible, all these matrices are invertible. So the product is invertible. So if A is a product of elementary matrices, then A is invertible, one way. Conversely, suppose that A is invertible and B is the inverse, so AB equal to identity. Okay, and what we want to show, A is a product of invertible matrices, right? If A is not a product of invertible matrices, then what will happen? If A is not a product of invertible matrices, then what will happen? That means the reduced row echelon form of A cannot be identity, right? So that means its last row must be equal to 0. A simple observation that if a matrix is not a product of elementary matrices, right, by multiplying, I can bring it to reduced row echelon form. Then what should happen to that reduced row echelon form? It cannot be identity, right, equal to identity. That means the last row must be equal to 0 in the reduced row echelon form. That is the only way it can happen. So let us assume the last row is 0, and let us say A tilde is the reduced row echelon form obtained from A by pre-multiplication of elementary matrices. Now if I apply AB is identity that is given to me, so let us apply A even matrices multiplied by B, right? So that gives me equal to, right? And this is A tilde, right? There is a B missing here. So this is A tilde B, okay? That is equal to E1, E2, En. And that means what? On the left hand side, if I look, this is a matrix, okay, which has last row as 0, which is a contradiction, right? Note that because the matrix B has got last row 0, right? So this is last row 0, that is a contradiction. So this is an elementary fact about the using elementary matrices. Okay. Okay, I think I will just skip that. Probably this can be looked into. Solution is already recorded, so you can look at the 2 by 2 matrix and try to write it as if AD minus BC is not equal to 0. What are the elementary matrices which make this product, right? Is row echelon form, reduced row echelon form equal to identity. So here is an exercise for the tutorial session. Write down as a product of elementary matrices. Okay. So how do you? So we want to check whether a matrix is invertible or not, and compute it inverse by elementary row operations. So the idea is very simple. So let us look at the idea. I think it was slightly. Let me see if I can. This red and color is blue. I want to make it slightly bigger, so yeah, this is okay, but where is the color? I want the color. Oh, what is happening?
Sir, can you please increase volume?
Yeah, volume, I don't know because I can increase speaker thing. I don't know volume. How do I increase on a laptop the volume?
Okay, okay.
Is there a possibility? I don't know. Tell me if a possibility, I will surely do it. Is it not the audible?
Sir, it is perfectly fine for me. Some students are writing in chat box, but I think the problem is on their side.
Okay, probably I will try to speak a bit louder, and that
Okay.
means I should drink more water.
Okay.
Speaking, okay. So let me. What I was trying to do was given. I am given a matrix A, okay, and I want to check. So to check if A is invertible or not, and find inverse if it exists. So just now we saw that for a matrix to be invertible, uh, it's so A is a matrix. Let us reduce it to reduced row equivalent form. So multiply by E1, multiply by E2, and I multiply by En. So that gives me its reduced row equivalent form. So let us call it as A tilde as the reduced row equivalent form. So what does the reduced row equivalent form look like? Right? If A is going to be invertible, just now we saw that its reduced row equivalent form should be identity, right? So it should be identity of the same order. If A is n cross n, then it should be n cross n. If A is n cross n, so that means that is an identity matrix, right? So that means if I call this as B, then B times A is equal to A tilde is equal to identity, right? So that means what? That means this B is equal to A inverse, right? So to get this B, which is A inverse, I have to keep track of this order in which I am doing the elementary row operations. So for that, whatever so write down A, and let us keep write down identity matrix. That is the target I am trying to reach. So I apply E1 to this, and then I apply E2 and so on. When I apply E1, keep track of it. So keep track of it. All so this is the record. That is a recording. What I am operations I'm doing. I am doing E2 here, then I will do E2 here, so on, and I will do E. I will do here, so that this becomes row equivalent form, and that is identity. and this will belong to some matrix B. Okay. So that is precisely what we are saying, that this matrix B is precisely obtained from the identity matrix by applying the elementary row operations on A that you are applying the same on identity matrix. And you could have gotten a matrix. Hello, can you switch off your mic, please?
You mute yourself. Okay.
Yeah. Right. So that gives us a process of checking. Take the matrix A, try to reduce it to row equivalent form, and keep track of the operations that you're doing. If you're able to achieve identity matrix, then the matrix is invertible and you get the matrix B as the inverse. So that is the process of checking and finding the inverse in case invertible by using elementary row operations. So let us do that. So this is the algorithm described just now, I said. So let us look at an example and do it. So let us look at a matrix, 3 by 3 matrix. I want to check whether that is invertible or not. So I am going to perform elementary row operations on this and try to find out what is the reduced row equivalent form of it. But whatever operations I'm doing, I want to keep a record of that and the order also in which I'm doing that. So for that, the record register, I keep the identity matrix here on the side, because that elementary matrix is obtained from identity matrix by that operation. So I will do that also. So here in this matrix, this is 1. So already a pivot is occurring here. I should make everything below that 0. So to make that 0, I should subtract R1 from R2, and that will make it 0. So I will do that on the whole thing. So I will consider this as a full matrix of 2n columns and same number of rows as A was. And same operation you do as you're doing here, same operation you continue doing on the identity matrix also. So once you do that, so this becomes 0, and when you subtract -4 and then you subtract, this is 5, and you subtract, this becomes -1, this is 1 only and 0. So that operation of R2 minus R1 was done throughout. So do that, so that is 1 0 0, and do the same now, make it 1 0 0. So let us by row operations, let us continue doing that. Okay, so 1 0 by those operations. So I leave the checking. So once you do all those operations, this becomes indeed an identity matrix. So the reduced row echelon form of A tilde is identity, and the same operations, elementary row operations with the same order if done identity matrix give you this matrix. So this matrix must be the inverse of A. So we can say A is invertible because its row echelon, reduced row echelon form is identity, and the corresponding matrix change in I is inverse. So this is the way of doing it. This can be put on a algorithm on the computer because it involves only matrix multiplications, and that will give us whether the A is invertible or not, and if invertible, what is the inverse. So this is the first application of row equivalent form. Okay. So find, so I'm just skipping that. More examples because they're all computational. You can try to check that inverse comes out to be, and one can verify actually that is a inverse. You can multiply out and see A multiplied by this is identity or not. You can verify the results. Okay. All right. So let's now look at what is slightly more theoretical knowledge about our work that we are doing. So if A is M cross N matrix and A tilde is its reduced row echelon form, then the rank of the matrix A is the number of pivots in A tilde. Actually, the number of pivots in A or a row echelon form will be same. So one doesn't have to say find out the reduced row echelon form. You can take the row echelon form itself. The number of pivots, P1, P2, PR. Okay, this is the number of pivots. R is the number of pivots. So that is called the rank of the matrix A. And for that rank is less than or equal to m, also less than or equal to n. The number of pivots, if you recall, we had said is less than or equal to both the number of rows and the number of columns. So this is, we are just given it a name instead of saying every time the number of pivots. That is called the rank of the matrix A. So here is the application of row echelon form to solving system of linear equations in terms of, so what we do, we look at the matrix. This is a system. If you recall, system can be written as AX is equal to B. Okay, A is the coefficient matrix, X is the variable, okay, vector, and B is equal to B. So that's what is given. And let us look at construct, add this column B as a new column to A. So augment it, add it. So to A, add one more column B, which is the coefficients on the right hand side of equality of the system of linear equations. So we got two matrices A and A plus. A is M cross N and B is M cross N plus 1 because one more column has been added. Okay. So the system has a solution if both have rank equal. That means when you are doing these row operations, you don't get a equation 0 equal to something non-zero, right? So that means what? That means the rank of A is equal to the rank of the non-zero rows in A are same as number of non-zero rows in A plus. So that is same as saying the rank is equal of the two. So rank of the augmented matrix is equal to the rank of the original matrix. Then the system has a solution, right? And if the number of if the rank number of non-zero rows in R and in R plus, in A plus is both equal to n, okay, that means each pivot will be each pivot is corresponding to a variable. So each variable can be uniquely determined if number of non-zero rows in A and A plus are same. So that is the rank. Okay. If the rank is less, okay, if the rank of A is equal to rank of A plus, system is solvable, but the rank is less. That means what? There will be a row which will be having something like A, AR some coefficients equal to something, right? So, and that R will be less than N. So there will be a equation which will involve more than one variable, equation involving more than one variable, right? So that will means what? Say for example, it involves two variables, then one of the variables can be given an arbitrary value and the other one can be computed. So essentially it says that if this rank is R, which is number of non-zero rows is less than N, then there will be N minus R independent variables. And what you do, the variable which has the pivot, that is determined in terms of the non-pivotal variable. So there's just a convention we make so that we can put it in an algorithm and everybody understands. If there is a equation involving a pivot equal to something, then the variables other than the pivotal variables are given arbitrary value, and the pivotal variable is computed in terms of the other variables. So this is so this gives a complete set of Gauss elimination method. So this method gives a complete solution. let us see if I can. Well, I'll just discuss the proof, so I won't go through the proof here. You can write down everything. As I said, n minus r free variables will be there to write down the solution. So this is in a nutshell of a rank of a plus. Right, rank of a plus is more than rank of. Then there is no. There is no inconsistency, no solution. Rank is strictly less than infinite, and rank equal to, and there is a unique solution. So this is the application of Gauss row echelon form to solving system of linear equations. It gives you all possible solutions. So one can write these results in another form, that a n cross n matrix, the following statements are equivalent. A is invertible. The equation Ax is equal to 0 has only trivial solution. Okay, both are equivalent statements, obviously. If row echelon form of A is identity matrix, invertibility means it is identity matrix, and that is same as saying the rank is equal to n, and that we saw is same as equivalent to saying A is a product of elementary matrices. So equations, this is normally called a homogeneous equation when Ax is equal to 0. Okay? That is the homogeneous equation, the only trivial solution is there. Now we'll come to homogeneous system just now. So this is the various forms of writing when is a matrix A invertible in terms of the rank, in terms of the elementary matrices, in terms of the sum of equations. So just now we said homogeneous system. So if in a system of linear equations, the coefficients b1, b2, bn are all 0, then that is called a homogeneous system. Solutions of general equation Ax is equal to b and solutions of the homogeneous system are related with each other in an obvious way, that if something is a for a homogeneous system is always solvable because x is equal to 0 is a possible solution. But I wanted to say that for a general system, okay, so let me probably write that. It's not there. So if you have got a system A, x is equal to b, and let us say x1 is a solution, x2 is another solution. So that implies ax1 is equal to ax2 equal to, both are equal to p. So that implies a applied to x1 minus x2 is equal to 0. So if x1, x2 are solutions of the system, then x1 minus x2 is a solution of the homogeneous system. Okay. So this is how homogeneous system solutions are related with the, so that is x1 minus 2 is a solution of homogeneous system. Okay. So finding solutions of the non-homogeneous system is equivalent to finding solutions of all solutions of the homogeneous system. And one particular solution is good enough to find, if you find a particular, sorry, a xp is equal to b, a particular solution, and x1 is a homogeneous solution for the homogeneous system, and axp plus x1 is equal to a applied to xp plus a applied to x1, and that gives you implies AX2 is equal to B plus that is 0, that is equal to B. So that means what? That if you have one particular solution of the non-homogeneous system and you have solutions of the homogeneous system, you add, you get all possible solutions of the non-homogeneous system. So that makes the homogeneous equation AX is equal to 0 more important. So let us write down for a M cross N matrix, the solution set of the homogeneous system, let us write it as N of A. So these are all elements of Rn such that when written in the matrix form, AX is equal to 0. So this is called a null space of A. So we are associating a special space with respect to the matrix A, and that is called the null space. So if A is M cross N, A is M cross N, then the null space is a subset of Rn. So number of columns Rn is a subset of Rn. This is a subset of Rn. Okay. Why it is called space becomes obvious if I just say that next property that okay, this is what I said that for Ax is equal to B, all solutions are given by x0, some particular solution plus a solution of the homogeneous space. So if I know what is the null space for matrix A, then I know solutions of the non-homogeneous system also completely. So we would like to know what is the null space for a matrix A. So we have defined null space for a matrix M cross N. N is the number of columns. So null space is a subset of that. And obviously it is quite clear the list of all solutions is what is the economical description of the solution set? Is the question. So how do I describe the solution of the homogeneous equation in a most economical way? That is the question we would like to tackle. Okay. So to do that, let us make an observation that the null space has got the following property, that if x1 and x2 are solutions of the null set N of A, right, then alpha x1 plus beta x2 is also a solution, is also in the null space. And that is obvious because if A is equal to 0 and AX2 is equal to 0, then A of alpha x1 plus beta x2, that will be alpha times ax1 plus beta times ax2, that also will be equal to 0. Right. So this leads to our next definition. This motivates one to consider those subsets of Rn which have this property. So this is what is called a vector space. We are looking at those subsets of Rn, okay, which have the property that if I take two elements in that subset V, then and alpha and beta are real numbers, then alpha V plus beta V also is in that. It is closed under linear combinations. One would like to say that. So in that sense, if you like to call this, if you find your previous knowledge is obstructing you to call it as a vector space, you can call it a vector subspace of Rn. That helps you. So we define what is a vector space. So let us look at N of A, the null space is a vector space in Rn. If any matrix, null space has that property that if x1, x2 are elements in the null space, that means ax1 is equal to 0, ax2 is 0, then alpha x1 plus beta x2 also is in, has the property A of that is 0. That means that is a vector space. Null space is a vector space. Okay. Let us look at another one which is slightly different. Look at ARN. What we are looking at is looking at all element sets and applying the matrix A to it. That gives you a new element. And where is this AX? If A is M cross N, X is in Rn, so we write it as a column vector N cross 1. So the product AX will be a column vector of order M cross, right? M rows and 1 column. So that will be any element of Rn. So ARn for a matrix M cross N is a subset of Rm, the number here is the number of rows. Okay, and that also is a subspace that is quite easy to check because if we take two elements, say y1 and y2 in this set, then y1 is ax1, y2 is ax2, then alpha times y1 plus beta times y2 will be the image of A times alpha x1 plus beta x. So it has that property that linear combinations are inside it. Okay? Let us look at the set alpha x belonging to R2. I think this is a time for me to take a breather for a minute. Dilpreet, I would like to ask participants geometrically, what does this look like?
Okay.
What is a geometric description of this set L?
So Sandeep is telling that this is line in R2.
Right, great. This is equation of a line in R2. Okay, you might have seen in coordinate geometry and so on, y1 plus y2, ax1 plus by2. Just now you saw linear equations give you lines. This is another way of writing the vector equation of a line in R2. If I take a x in R3, that will give me a line in R3. Okay, and we can have a line in Rn. Okay, if I take x in Rn, so we can define lines in any Rn that way. Okay, great. Line passing through with the okay, alpha x. Here is now we're starting with the linear combinations and linear span. Just now we saw that if x1, x2 belong to the null space, then x1 plus x2 belong, alpha times x1 belong, and so on. So these kind of things are called the linear combinations. And the set of all possible linear combinations put together in a box is called a linear span. So we'll start with the definition that given vectors v1 to vk in Rn, scalars alpha c1, c2, ck in R, look at the combination c1 times v1, that is again a element in Rn, c2, v2, that is again an element in Rn, right? And add them up all, you can add them. So that is called a finite linear combination. So such a thing is called a finite linear combination of elements v1, v2, vk in Rn. And all such linear combinations put together give you a set which is called LS or called the linear span of the set S. You take any set, okay, S in Rn and linear span, if you call this set as S, okay, then this is the linear span of. So what is the set S here? This is the set of the vectors v1, v2. Okay. That is the set we are taking. Okay, the linear span of it, all finite linear combinations of elements of S. Okay, so pick up finite number of elements. Uh, Actually, S could be any set. It need not be this particular finite number of elements. What you can do is take any subset S. So I think let me clarify probably something that I said just now. So let us take S, a subset of Rn, and pick up. So let V1, Vk belong to S, any finite number of elements of S, then you can have a linear combination of that. So for scalars alpha 1, alpha k belonging to R, you can have a linear combination which is alpha 1 v1 plus alpha k vk. Okay. Uh, and where v1, v2, vk belong to S, k is bigger than or equal to, you can take any finite number of them, and alpha 1, alpha k belonging to R. So this is what is linear span. So we are not restricting S to be only a given finite set. S could be any set. Okay. But pick up any finite subset of it and take a linear combination. So we are looking at finite linear combinations of elements of S. So this is finite linear combinations of elements of S. Okay. So that is what is called the linear span of elements of S. Okay. So what we are claiming is L of S is a vector space. That is not very difficult to show. Okay. I think it's quite easy. Probably can be left as an exercise to show that the linear span of elements of S forms a vector space. If you take two linear combinations, their sum is again a linear combination, and the scalar multiples are again linear combinations. Right? So consider, let us take a line along this. Okay. So consider a line passing the origin along the vector 1, 0, 1. So what is a linear span of that? Just now somebody said if you take, this is a vector, if you take alpha times that, that is a line. So linear span is a line actually. Okay. So linear span of one vector is a line along this vector 1, 0, 1. Okay, minus 1. So it will be in that direction. Okay. Let us take vectors v1, v2, v3, which are which are in three vectors. There are three vectors. Each has got two components, and S is the set of v1, v2, v3. So let us explore the following. Uh, I I think this could be. Let us do this exercise now. Show that L of v1, v2 is same as the span of v2, v3. Everybody tries to show it in your notebook, and if you are able to succeed, say that yes, I am able to prove it. Then I will ask you, how did you prove that the span of v1, v2 is same as span of v2, v1? 2 minus 4. So let me write 2 minus 4, that is v1. What is v2? v2 is 1, 9. And 9, and v3, oh sorry, v3 is equal to 3, 5. And we are trying to see, can you say that linear span of v1, v2 is equal to linear span of v2? What is the first question? v1, v2, v3. So that is the question. I will keep a track here. Dilpreet will tell me how many are saying yes, how many are saying no.
Okay.
Dilpreet, as soon as you get one answer yes, tell me. As soon as you get one more answer no, please tell me.
So many people are saying yes.
Many are saying yes.
Yes.
Okay. So you pick up randomly, toss a coin, you pick up someone to explain who said yes, why L of V1, V2 is equal to L of V2, V3.
Okay. Vijay Kumar Salonki, please explain.
Vijay Kumar Solanki, please explain why do you say your answer is yes?
Have to unmute him.
Answer is yes, because
Can you please type in the chat?
well, you can say orally. I will accept oral explanations. Actually, I want to listen.
So it's I have to unmute then that will give.
There is a problem unmuting.
No, now they can unmute. You can unmute now. Please, Vijay or Salanki, please unmute yourself and explain. Okay. Jaya Kumar, do you want to explain?
Yes, madam.
Jaya Kumar.
Yes, yes.
Yes, please unmute.
Vector V3 can be written as sum of V1 and V2. So
V3 can be written as a sum of
V1 and V2.
V1,
V2.
just V1 plus V2 straight away, or you want some modification?
Yeah, alpha 1 V1 plus alpha 2 V2. Alpha 1 is 1.
Alpha 1 is 1.
1 into V1 plus 1 into V2.
What is the coefficient of V2 you are putting?
1, 1,
And V1?
1.
But V1 plus V2 is equal to V3. So 2 plus 1 is 3. Oh yeah, good, great.
And also
Okay.
V1 can be written as V3 minus V2.
Okay.
And here also the alpha 1 is 1 and the
Yeah, fine.
alpha 2 is minus.
Okay, good. So basically, I thank you.
Yeah, thank you.
Yeah, it's good enough explanation. Perfect. So what you are saying is these two are same because I can write V2 is already there. I can write V3 as a combination of V1 plus V2. So V3 inside. So all linear combinations of that will be inside. And similarly, the other way around, V1 is equal to this, so that the combinations will be inside. So good. This is a very simple thing we have given you, because here you can just observe and write down the combinations. Okay. In general, if you want to check, okay, so let us try to check the last one, namely the following. I want to check that the linear span of V1 and V2 is the same as whole of R2. I want to check that. L of V1, V2 is same as R2. So somebody will explain that L of V1, V2 is equal to R2. Is 2, 4, that is V1, and V2 are equal to 1, comma. Okay, so let me, I think let me go ahead without spending some time. I would have loved to sort of see reactions of audience. But anyway, this part is quite clear that this is a subset of it, right? Because you're adding linear combinations of elements of R2, so you will be in R2. To show this other way around, so let's take something alpha beta in R2. So I want alpha beta equal to x times V1 plus y times V2. If I can do that, then alpha beta is arbitrary. Then any element in R2 will be a linear combination of V1 and V2. So we'll get a equality here. So, but that means I have to write x times 2 minus 4 plus y times 1, 9. And that means I have to write it as, so this is 2x plus y, and this is minus 4x plus 9y. So that is equal to, Anil, aaj nahi chahiye. Okay, so let me write this as 2 minus 4, 1, 9 xy. So for every alpha beta belonging to R, to show some x and y. It comes down to this. And that is same as solving a system of equations. That is same as with this is the matrix A. So to solve this system, you will have to, a very simple example of 2 by 2 we are showing, you'll have to reduce it to row echelon form and then find out whether what is the solution possible. And we will show that yes, a solution is possible. So that is a way of showing. So let me go back, showing that all of this others are exercises. You can try to show that this is equal to R2. So linear span is whole of R2. But if I drop any one, I drop V2 and take only linear span of V1, that will not give me R2. Why will not that give me R2? For example, just now we said if you take one vector and take the linear span, that means you will be taking alpha times V1, and that is only a line. So geometrically, that will be a line in the plane, and all the elements outside the line will be left out. So the span of these different sets is equal to R2, and you cannot drop any one of the vectors from any one of the sets, right? So what does that mean? So that gives us a something that how many elements are required to say that linear span will be equal to R2. So we are getting 2 elements at least are required. We have got illustrations of 2 elements generating meaning the linear span is equal to R2, and I cannot cut back. So that gives us a definition of what is called a basis of a vector space. For a so for a set in Rn, okay, a subset V of S is called a basis for the vector space V. Of course, we are in Rn. So if it spans L of B, the linear combinations of elements of B is equal to V. Every element in V is a linear combination of elements of B, and you cannot cut short, and you cannot make it smaller. That means no proper subset of B will have that property. In that case, this set is called a basis for the vector space. So you can think of basis as a minimal smallest set of smallest generating set of vectors in the space vector space. Okay, so you can have examples. For example, just now we saw those 3 vectors, right? Any 2 of them generate R2, and none of them can be dropped. So each one of them is a basis for the vector space. So what we are saying that to construct whole of R2, we need only two vectors. For example, V1, V2, or V2, V3, or V1, V3. And everything else in R2 is built as a linear combination of elements of R2. So that, and you cannot delete any one of them. So that is not the minimal set. This is a minimal set. So this is the least amount of information you should have to get everything about R2. So this is what is called a basis of the vector space. Uh, Dilpreet, how much time do you think we have more?
Uh,
Hello. I
I
think
think
only
I'm saying like 4 5.
yeah.
Yes, 4 to 5 minutes.
So I don't think I can prove a theorem which I want to say that. I think I should do it next time. Uh, Different ways of describing a basis. But one thing it seems quite clear from here that though there are different bases possible for R2, each one of them has got two elements. So the number of elements in each base is same and we cannot cut it short, right? So that is something called the dimension of the vector space. So we'll dimension and other ways of describing the basis of a vector space, we will do it next time. Uh, Remaining 2 3 minutes, I would like, if anybody would like to ask a question, then I would like to respond back.
Yeah. So this request came earlier also. Students are asking that if you can provide lecture notes to them.
Oh, great. Okay. I think my recordings itself should be the lecture notes.
Available on YouTube to watch
Yeah.
again.
But let me just, I think this may sound like self-publicity. There is a book called, uh, okay, let me write from geometry to algebra. An introduction to linear algebra. This is published in India by NA Books. So one possibility, because it's very difficult to say that buy this book, because in the current scenario, this book you can't go to a bookshop and buy it. Maybe you can try it online if it is available. That is one possibility. Or try uh, go to the site called Math for All.in. I think let me probably see if I can go there now and show you. Oh, how do I change? Okay. I think let me change my orientation from tablet to the laptop. Try to enter here. Is it my screen still visible?
Yes, sir.
Okay. So www. Oh God, it's not typing. www. I'm trying to give you a online resource. Possibly. So go to this section called Math for College. scroll down, you should see, yeah, I think here it is. There is something called, yeah, you see those, all that I am going to describe is more or less in that book, Geometry to Algebra, detailed content. Yeah, this is yes, you can say a soft version of that book that I just now said. You can buy that book as and when convenient, probably if you want a hard copy. Otherwise, you can just go online and look at the contents. So it more or less gives you everything that I'm talking about. So you can click something and it will take you there. You can read it. The only thing is because at that time Java was I think Java programming. So many things like these applets are made in Java, but they may not work because Java is not accepted by many browsers. So you may have a problem about that, but otherwise the written content you can always access from that. So Math for All, go to that page, detailed content, geometry to algebra, and you will find a soft version of it available. I think more than that, Dilpreet, anything else you think I should be offering them?
They are asking if PDF of book is available.
The publisher will kill me.
Okay. Okay.
I think a PDF version of the book is available from the publisher itself.
Okay.
That is what they call it as e-book nowadays.
Ebook, yeah. That
Yeah.
Kindle version.
Kindle version probably, and it's cheaper probably. So try it. Okay. If you don't get it, then probably I'll try to call him and say whether it's available or not. Kindle book. I think
Okay.
Amazon has a also had a sort of Amazon in book store. I don't know. Please try.
Okay.
For the I cannot give you PDF of the book because I have cut my hands by writing a copyright contract with the publisher. Okay. But I am giving you a kind of a soft version of it, which probably you can download and do something about it. I don't know.
Okay.
Okay, there was a course. Okay, I think let me stop here.
Okay, thank you. I would like to announce that tomorrow lectures will start at 5 p.m., not at 5:30. So tomorrow we have two 1 hour lectures. So first lecture is from 5 p.m. to 6 p.m. and second lecture is from 6:15 p.m. to 7:15 p.m. So tomorrow we have two 1 hour lectures. Okay, so please turn up at 5 p.m. tomorrow.
And keep eatables nearby if in case you feel hungry for 2 hours.
Okay.
Yeah.
Okay. Is there any other question? Okay, if there is no question, we are ending this meeting now. Thank you for joining this meeting. Thank you, Professor Rana, for wonderful telling us math for again.
Dilpreet, you don't have to say thank you every time. It's okay.
Okay. Okay. So see you all tomorrow. Bye.
Yeah. 5 o'clock. Fine.